No.
You're on there.
As I mentioned, my talk is on Magnus experience for nonlinear Schrödinger equation.
Funny title.
And the goal is to see if we can start some kind of collaboration between members of the program. And in particular, we are focusing in a subtopic that is in different kind of Schrödinger equation. And I will try to analyze different techniques in order to solve a number of problems, in order to see if we can start some kind of brainstorming and to think if we can start some kind of collaboration. In particular, I had to focus in some kind of problems that will be the numerical integration of several nonlinear Schrödinger equations of different nature, and we will explore if it would be interesting to look for efficient algorithms using algebraic technique in which many of the people of the program are familiar, and to see if we can generate some kind of new algorithms or new ideas in this kind of topic. So it's a different talk to standard talks where I'm not going to present the results of my last paper. Is that I will try to start new problems in order to see if we can find new ideas and new collaborations. So one of the problems in which I will focus is in the Gross-Pitaevskii equation, where I will consider it's like the Schrödinger equation, where we have a potential that can be also explicit and dependent. The time dependency can come either because there is an external field acting on the problem, or because we are making some kind of change of coordinates that makes the system time dependent. For instance, if there is a magnetic field, in this magnetic field introduces a term here that involves derivatives and positions, and maybe it's worth to make a change of coordinates where this spatial derivative disappears, but then introduces a time dependency. But this is the case. And we have here a nonlinearity. Another problem in which I'm going to consider or to study is the Kohn-Sham equation, where it looks like the previous one, but now here it contains what is called the Hartree exchange correlation potential. This is some kind of model to analyze problems in which there are many particles, and we cannot use a standard Schrödinger equation because it will be too expensive to use standard methods. So one needs some kind of models where this is the density of the function that involves this kind of probability function. And the last problem in which this will be for the case in which there are a number of n particles. We are going to this. And the last one is the quantum optimal control problems, where we have a Schrödinger equation where we have the kinetic potential. In this case, I will take the potential as a time independent because the time dependency will come from an external field that is time dependent. Because I want to have a control on the quantum system in order to take it from one state to a different particular one. Here, this dependency on x is fixed because this depends on which device you have, if you have a laser or whatever, but you have a control on the intensity. So this time dependency is the intensity you can control by changing this, and the goal is to maximize a given value. Where if O is an operator, to maximize this operator, and where O could be a positive definite function, and we will try to take the wave function from the initial conditions to try to maximize this overlap. It's like to move the solutions to this position that is obviously we cannot overlap 100% because maybe with the laser we cannot attain this purpose, but we can try to maximize this result in an optimal way.
The capital T in the box, is that the same as?
Is the final time.
And up above, one line above?
Sorry, this is the kinetic part. This would be like this one. This.
It's just an abbreviation for the box.
Yes, the kinetic, sorry, for using the same letter. Is this term, but it's the kinetic part because it's usually used T in classical mechanics.
Yeah, fine. No
T and but this is Laplacian. And this T is the final time where you suppose that And the goal is to find which is the function in which we have a control that reaches this goal. I must say also that recently these two problems also I studied with some kind of control. So there is also an interest of control problems in the Gross-Pitaevskii and in the Kohn-Sham equation, in order to see if they can be controlled. So at least seems like these three kind of problems sound quite interesting to be analyzed to see if we can find some kind of algorithms that perhaps improve the state of the art on these kind of problems. With respect to the Gross-Pitaevskii equation, I will briefly mention some kind of techniques that have been used, and later I will mention some of the techniques that perhaps could be used that in some cases could lead to more efficient schemes. For instance, some schemes that can be used to solve this Gross-Pitaevskii equation are, for instance, splitting. In this case, I will call it computational methods, where it can split this into, this will be like the kinetic part and this will be like the potential. Because this system can be solved in two parts, well, can be split in two parts, where this one can be exactly solved, or if the problem is periodic in the momentum space, this is diagonal. This term is also diagonal in coordinate space, because this value, when there is no kinetic part, this is kept constant. So this term is exactly solvable, even if it's time dependent. The only thing is that we need to complete an integral, and we can use some kind of splitting. And the same time, splittings that are formed from methods, because there are some kind of commutators that vanishes, and then we can use some more efficient schemes. The only problem is that when using this kind of splitting methods, the time has to be advanced according to the coefficients of the method, not at the times you wanted to compute this time dependency. But another way is to split this potential into a quadratic part and a remaining. This can be done, for instance, with some kind of Magnus approximation. This term can be solved exactly in many different ways. We solve it using Fourier transform because it allows a simple split, but there may be other ways to do it, or to be analyzed, this kind of splitting. And another one in which we have been working very recently is even in the paper by the special issue for Quizflow. We built some kind of averages over this time. This is explicitly time dependent, but we can take some kind of appropriate averages on the time, where we evaluate this potential at the times we have a good, well, we think is the best. Maybe we can use different orders of accuracy in the time. Once we have this, we can use maybe one splitting or whatever, but for autonomous problems. So these are some kind of the tricks or techniques in which we have been using, and some ideas that we are considering that perhaps could be useful is to consider the Gross-Pitaevskii equation, but now to take this nonlinearity, for instance, suppose that we can find a time-dependent function that approximates this solution. If we plug it here, automatically this turns into a linear Schrödinger equation. But for linear Schrödinger equation, we have many more techniques than for the nonlinear one. So we will have to think about the possibility of finding a good approximation to this function in order to linearize this, and to use the traits or the techniques, algebraic techniques we know for linear problems, non-autonomous linear problems, using different kind of Magnus trick and Magnus and some kind of splitting and composition and so on that are built for this problem. So this approximation will allow us to use algebraic techniques for linear case. For the Kohn-Sham equation, well, there is one thing that I would like to point is that the paper by Kohn-Sham from 1965 has more than 54,000 citations in Google. So this is a good thing in the sense that, okay, this is a hot topic. Every year there are more than 3,000 papers citing this one. So it seems like many people is very much interested in this topic. The bad thing is that how to generate something new in this field that has not been done in any of these 54,000 papers. So it's something that, okay, we can work in this, but at the same time there are many things that have been done. So let's see if it is possible to do something, at least in the numerical integrations. And I guess that most of the interest is in physical models and so on. So one thing that has been done is to take this function that is the nonlinearity and to take it as a time-dependent function. But this value is taken from previous solutions. So we are integrating in step in so it stores the result from previous steps. Then this gives you an approximation to the value of this function in the interval. Well, this has been done in this very recent paper. That at the same time, this is a second paper from 2004, where they were testing many different methods from the CUTM of the step, implicit, explicit, even many exponential integrators. At the end, they concluded that this one, the fourth order commutator free method, using these two values from this interval that are obtained from a few previous steps, from previous values, was the most efficient scheme among a huge list of methods. Similarly, I saw that, okay, this can be improved very quickly or very easily because we can use even more efficient commutator-free methods or other kind of Magnus integrators for this kind of problems. So more efficient Magnus integrators can be also used, but obviously if we introduce more efficient schemes, this implies that we need more accurate values of the density function. This means that we need values of this from many previous steps. And this is a big problem. It's a big problem because if we take in this approximation, here we are approximating this by previous steps, the value from previous. If we take many previous steps, this means that we are introducing large errors and at the same time make it the algorithm unstable. Well, but it produces very accurate results, but there is a problem, is that we are in a collaboration with some other people from that paper. We were analyzing, well, the Kohn-Sham, but coupled with nuclei. So this is the classical quantum problem. Well, at the end, it's roughly the same. It's the Kohn-Sham equation coupled with nuclei, where this one depends on the position of the Q and P are the position amount of the nuclei, and this is the equation for the electrons. And at the end, it's roughly the same. They are coupled, and we were using not the fourth order, but higher order methods, more efficient schemes, and then they were forced, in some sense, to use many previous higher order approximations with many previous steps. And at the end, this is some kind of performance plots. This is the exponential midpoint. Then this is the accuracy in logarithmic scale. This roughly to give the idea of what was happening in the experiment. This is the accuracy. This is the computational cost. So the best method should be the one that is more in the left-hand side and down. So I was proposing some kind of schemes that are much more accurate, but since they recreate values from many previous steps, then when the time step was relatively large, the error exploded. Because that was not was very accurate for high, well, if we wanted high accuracy, these were the best methods, but for medium to low accuracy, these were not the best. So the question is, are there alternative procedures to find better approximations to this function in this interval, so we can, in some sense, like take these kind of schemes and to move it until here? That will provide many more accurate for medium accuracies. So this will be one of the open problems that we can analyze. In the quantum optimal control problem, we have this problem to be solved, where this is for instance, an external field that can be a laser, where we have a control of the intensity of the laser. So in this case, I will focus in one particular problem. For instance, suppose that in this case we have to maximize the overlap of this function because we want to move the initial conditions to a final solution that maximizes this integral, so that maximizes the overlap. But we have to penalize with a cost. So this is the energy we are paying of our laser. So it's penalized with this and with another term that is the Lagrange multiplier. This that tries to assure that the Schrödinger equation is satisfied. So alpha 0, alpha naught is a positive parameter to chosen to weight the significance of the laser energy. This O is the positive definite operator that is used to attack the wave function. Okay, the goal is not in order to use or to the theory of optimal control problems is suppose that in this case we want to maximize this. So when this operator function, when this derivative is 0 or the maxima occurs when the intensity of the laser takes this value. But this value depends on these two guys, and these two guys are the solution of this problem. So we need to solve this problem in order to find who is the intensity of the laser that is optimal for this problem. But what is the problem of this? This is a coupled system of non-linear, because there is non-linear Schrödinger equation. But at the same time, this has initial condition and this has some final condition. So the thing is, okay, how can we build schemes for solving this kind of problems? And which kind of methods can be used for solving this kind of schemes? But be careful about one thing is that this is a final condition, but notice that this is not known because this value is not known. So we need to integrate this when arrive here, because that this, if we integrate it forward this one, we should arrive to this point. So it's not so trivial. So there are several ways to do it. People are using some kind of iterative schemes where they integrate forward and backward and try to converge. And typically the schemes are lower than methods, first or second order method. But when analyzing the techniques that are used, they look like this kind of scheme should be improved or could be improved using more techniques, because then we can some kind of linearize this term, making it time dependent, and to use some kind of trick from Magnus integrators or from splitting or from this kind of things. In this case, there are two steps that are required. First is to find one procedure that, in an iterative way to know which is the most appropriate iterative procedure. And then at each iteration, we have to solve both coupled equations. So we need to find how to solve this by perhaps linearization in an efficient way. And there is a remark is that, okay, since we usually an iteration scheme, it's started with an initial guess, okay, the first iterations we don't need to use a very sophisticated scheme. We can start with a low order scheme, with a cheap scheme, and as we are approaching to convergence, we can use a more elaborated, more costly scheme. And one procedure that maybe could work is to linearize and store some values from previous iteration to improve convergence. So that is what is done. But when we store things from previous stages, we need to store something that is cheap to store. Not to store the wave function of all the integration, because otherwise it could be too expensive. So to see what can be stored that is useful for the next iteration. Well, in all previous methods, of all examples, I'm considering all the Schrödinger equation, at the end, the structure of the differential equation is this one. It's a nonlinear differential equation when we discretize. And what I'm trying to mention is, okay, we want to analyze what happens if it could be convenient to solve instead a non-autonomous linear equation where a of t is an approximation to this one. So, but then we have to find which is the best approximation to this function here. It's like the x coordinates are split in two. One is treated differently to the other one. So because this x is treated differently to this one. No? But we need to find how to treat it appropriately. Then, if this is possible, we can use Magnus splitting and composition techniques to solve linear problems. And these techniques have shown to be very useful for solving many problems, and they could also be useful for solving, in this case, the previous Schrödinger equation that we were mentioning. I will now, since we want to solve this problem, I'm not going to introduce some kind of techniques in which some of you are familiar, but since not everyone is familiar, I will introduce maybe from, not from the beginning, but at least I will focus in one case, and I will show you some kind of generalizations. So I will consider now the 6 order schemes in order to see how the Magnus integrators can be applied for solving this kind of problems, and how some tricks can be used to solve this kind of problem. So I will focus in 6 order schemes. So let's consider the 6 order Gaussian quadrature rule, that are these 3 nodes. Now let's consider the Legendre polynomials that takes values 1 or 0 at the nodes. So this for value of C1 this is 1, and for C2 or C3 this is 0. So this is no. Now let's consider this interpolating Lagrange matrix polynomial that is this matrix. So this A1 corresponds to the value of C1. So for the moment I will take t, the time between 0 and h for one time step. So without loss of generality. So this is an interpolating polynomial. But in principle, this is, since L is quadratic in sigma, this is a quadratic polynomial. So we would expect that if we consider this problem, this is a quadratic approximation. So this should be a 3rd order approximation to the previous one. So the solution of this problem I would expect to be of order 3, and a 3rd order approximation to the exact solution. But it's a 3rd order approximation during the whole path until we reach the end. But at the end, it's not order 3, it's order 6. So if we compare this, we want to solve this problem. But instead, if we solve this one, during the whole interval, it's order 3, but when we reach to the end, it's order 6. Well, this is related to what the pioneering papers by Arjen is related to what you have done in this case. So instead of this, we will solve this quite simple equation that is only quadratic in time, because we will get a 6th order approximation at the end. At the same time, let's see this fact. Let's consider this one-dimensional integral, and we approximate this using the 6th order Gaussian quadrature. So this is this, that is well known, up to order 6. But we can repeat it for this integral and for this integral. This can be seen as momentum integrals, but this integral is this value, and this integral takes this value. Okay, so let's make linear combination from this, from all errors here. We can write all this in terms of these 3 momentum integrals up to order h7. So at the end, I will build some kind of schemes that will depend on the quadrature rules of this, but I can rewrite everything in terms of one-dimensional integrals. And each one-dimensional integral can be approximated by any quadrature rule I wanted. So any method I will write can be written in terms of any quadrature rule, or even in terms of one-dimensional integrals. And the question is, all methods we obtain can be written in terms of one-dimensional integrals, and is it really? In which cases is this advantageous to compute one-dimensional integrals exactly instead of evaluating or using the values of the matrix in a quadrature rule. Maybe in some cases it's better to use one-dimensional integrals, compute exactly this one-dimensional integral, and we get more accurate results or cheaper or whatever. At the same time, once we build a method using a given quadrature rule, automatically is written for any quadrature rule, just with this change of coordinates. And this has been done also for linear and non-linear problems. Now, in order to build efficient schemes, it is convenient to work with a graded algebra. This is from a pioneer by Kohn-Sham and Vigneault. And okay, let's write this matrix that is quadratic in time. Remember that before I mentioned this, but instead of writing in powers of t, I will write it in powers of tau, that is t, but shift to the center of the integral, because I want to make it symmetric. So we can write this matrix in a Taylor expansion about the powers of tau. Tau is the value of time at the center of the interval. So alpha 1 is just the value of this matrix at the midpoint. This alpha 2 is like the derivative of this matrix, of the interpolating matrix at the midpoint, and this is the second derivative. This is order h squared, and h cubed. So all methods can be written in terms of alpha 1, alpha 2, and alpha 3, and everything simplifies enormously. So instead, if we use the Magnus expansion, it's the expansion of this term, contains the integral of this one, but all these integrals, if we plug it here, can be computed analytically. So everything is analytical. At the same time, if we write in terms of this gradient, it's very simple to know which terms are survived up to a given order. And they are exactly the independent terms that will appear. So up to order 6, these are when we compute the integral of omega, this integral is alpha 1 plus 1 over 12 alpha 3. These two terms come from the second integral, but they are analytical and are trivial to compute. And then we build an scheme up to order 6. But this is not the method that we are going to use next one. We will take this as the formal solution. So we have the formal solution, and we will try to build methods that approximate the formal solution. Then we need to start to analyze what we have here that can be easily to compute it, and what is not easy to compute. And we will find several tricks to avoid the difficult parts while keeping the cheap ones in building the scheme. And for a given problem, we should look for the elements that can be computed efficiently and to approximate the formal solution using composition of these terms, or the cheap terms. Terms that can be easily. And let's start with the Schrödinger equation, the linear one. Suppose that we have the linear Schrödinger equation. This is the Laplacian, this is the potential that depends on time. And then remember that alpha 1, alpha 2, and alpha 3 are the derivatives of the interpolating polynomial, matrix polynomial, at the midpoint. This was, remember this, alpha 1 is the value of this at midpoint, alpha 2 is this difference, but when we have this in alpha 2 and alpha 3, if the matrix A has a constant part and an independent one, the constant will disappear here and here. The constant part only will survive in alpha 1, and all other terms will disappear. So T, the Laplacian, survives only in alpha 1. In alpha 2 and alpha 3, all of them are functions depending on the potential. So they are diagonal in coordinates. So this means that the exponential of alpha 2 and alpha 3 is diagonal and then is trivial to be computed. But not only this, because once we have this structure, we think profit that in addition this commutation of alpha 2 and alpha 3 vanishes, because they are diagonal for this particular problem. At the same time, since alpha 1, the kinetic part, is quadratic in momentum, this term depends only on spatial derivatives of the potential. Then this is diagonal too. We can benefit from all these results in order to build new schemes. But I'm just trying to see that, okay, new ideas that perhaps for different problems we can use many different things. let's see in an example how these kind of things can be manipulated. Suppose that instead of order 6, let's simplify and it's an order 4. The order 4 only contains these two terms. This is order h, this is order hq because alpha 1 is order h, alpha 2 is order h squared. So this is order hq, this is order h. And suppose that this is a fourth order approximation and we are using a fourth order quadrature rule. And we can approximate this exponential in many different ways, and the most appropriate will depend on each particular problem. So I'm not saying that the best method is this one. So we have to analyze our problem and depends on the problem. So for instance, this is the formal solution. Okay, let's consider this will be like an splitting method, symmetric one. Okay, this way it's like the dominant part that is order h, we are split it in two parts. And this one is kept, but this step is ordered HQ and maybe it can be completed efficiently. But we can do different things. It's not necessary to split into parts that appear here. Alpha 2 is not here, but since alpha 2 is diagonal, because here alpha 2 is a diagonal term, it's a cheap one, I can build this term, I can approximate in this form. Alpha 2 and minus alpha 2. Why? Because this is an even term. If I write it skew symmetrically, the whole scheme is symmetric. And approximate this at order 5. So this is diagonal, and automatically, at the same cost as alpha 1, I built a fourth order scheme. So this has the same cost as the exponential midpoint, but it's order 4 instead of order 5. And slightly more efficient schemes are if we distributed a mixture between this and this one. To split into 1/2 and 1/2, but to distribute it this way, and the alpha 2 distributed in this way. This produces even a more efficient way. And this is the fourth order commutator free that was previously mentioned, in which people for the Kohn-Sham equation, they say that this was the most efficient scheme for the problem or for the test they were using. Well, just to mention that for order 6, in the case we were studying, remember that alpha 2 and alpha 3 and this one were diagonal elements. All of them depending on the potential only. And they are diagonal. And the last one also diagonal. So we can build a 6th order scheme that contains only two exponentials that are like 1/2 and 1/2. So the cost is similar to this one, but this order 6. And the order 6 contains like the evolution of the one potential, half a step of kinetic one potential, half a step of kinetic potential, and these are averages of the potential. Different averages of the potential that are evaluated at the 3 nodes, or in terms of one-dimensional integrals, and this scheme, I must say that has been used to solve linear Schrödinger, but also non-linear Gross-Pitaevskii equation, and also Kohn-Sham equation. And was done with some success. It was working quite efficiently, this scheme. Okay, maybe not necessarily 6th order, but maybe different, this kind of tricks could be used to solve some of the problems in which we are.
So you are giving up palindrome.
It's not exactly palindromic because.
Exactly.
Because see, this is the alpha 2 that is contain an even h squared. This is with minus on with plus, with minus on. So this trick, yes, everything is time symmetric. So we it is. So well, I said that this talk was relatively short. So the idea was to propose different techniques, tools, in order to see if we can try to solve this kind of problems using these techniques or other techniques that we think they could be useful. I presented the Gross-Pitaevskii equation, where we can see if we can manage to linearize this in a proper way in order to use. Since I show you that, okay, using Magnus and composition for linear problems, we can maybe find quite efficient schemes. So since for linear problems there are some kind of techniques that are very efficient, if we try to linearize these kind of problems, perhaps we can use such a kind of schemes to performance of they haven't worked quite efficiently, but they are not optimal in the sense that they have some weakness, and we can see if we can manage to fix or to improve this performance, and also to see if we can do something on optimal control problems, because they are interested not only for the Schrödinger equation, but as mentioned also recently, they are interested for this kind of other problems. So the question is, can we use some kind of Magnus composition or any techniques that in which we are more or less familiar to build new algorithms with a proper linearization? So this is like some kind of other problems to see if we can start some kind of brainstorming, whatever. So thank you.
Okay, questions?
I have one question. You mentioned several times in your talks that some methods are more efficient than others. So the question is, how do you measure efficiency?
Well, the efficiency when solving a particular problem is that when you compare two methods, maybe this depends obviously on the skills of the programmer, and typically for instance in the Kohn-Sham equation they were using different methods. I'm not sure if they were using it in the best and the optimal way, but they measured from some kind of discretizations, they computed the cost, and at the end they measured they compare the solution, the numerical solution with respect to a reference solution. And
well, I'm asking because nowadays there is so many different hardware available. If your laptop, say, where you can measure things, but you can go to a parallel computer, either distributed memory, shared memory, GPU, and depending on where you run the code, you get completely different results.
Yes, I completely agree with you that.
Therefore, I ask.
I can say yes. Even in this, for instance, for the Kohn-Sham equation, they compare a huge number of methods, and if in addition you have to compare, obviously the way to compare are much is you can compare with many different things. So as you said, to analyze your GPU that you're expert probably for some operations are better, and even I think that a good idea would be to know or to build from the beginning some kind of schemes that optimize for some kind of operation. For instance, if GPU is optimal for doing this kind of operations, then to build a scheme that optimal in this kind of schemes. But I think there is many things to do in this direction.
No, I think it's a very good point because, for example, everybody, including me, is sure that Magnus is much better than Fair. But Fair can be put on several processors. So maybe in parallel architecture it beats Magnus.
Yeah. Once you change the objective function or the cost of the algorithms comes from different, then the optimal schemes can be completely fair.
Yes.
You mentioned that you described here the method how to solve the sixth order, how to use the sixth order method for linear equation. And earlier you mentioned that we can use it after a slight linearization of the nonlinear one. And at the very end you mentioned that you already applied this scheme to this Kohn-Sham and to nonlinear Gross-Pitaevskii. So what kind of linearization were you using there? This is the question. Because here I didn't see.
No, for the Gross-Pitaevskii we didn't do any linearization. Well, what we were doing it was an average of this time-dependent function. So we used some kind of at the end was roughly this scheme, but for nonlinear problems.
For nonlinear problems, but then
it's a different.
For nonlinear problem, and here potential was conservative, right? The potential was depending on time or not?
Yes. Well, in the problem we applied implied was time dependent, but this time dependency came because we make a change of coordinates that brought, because it contains a magnetic field that was time independent, but making a change of coordinates rotating with the magnetic field, this there was a momentum contribution here that can be cancelled at the cost of introducing a time dependent. So the coordinates were multiplied by a time dependent rotation, but at the same time disappear this. So what we were doing was some kind of aberration on the time dependency, but the scheme was still, the problem was still non-linear within linearization.
Non-linear, but then we have this time dependent because the non-linearity, right? How did you deal with this? Because my another question was to be, and maybe I don't understand something at the very beginning. At the very beginning, you were saying about at least 3 ways of dealing with nonlinear equations, and you were thinking about the splitting, and you wrote the paper with Philip where you were splitting the potential part into the quadratic part and not quadratic, and then it was stick to the other part, and you were using the splitting methods first, right? The splitting, and what I was confused later is because if you are splitting first something that is time dependent, then it means that we have second order method at most, right? Because the solution to the whole equation is given by a Magnus.
No, when we were using this kind of splitting, this is time dependent and this is time dependent. If you take the time as some kind of coordinate, you can, in some sense, like a second, to make it the whole thing autonomous. You take this time as a coordinate, and this and its associated momentum. Extending this in one is like extending in one more coordinate, and you put the momentum in this part. This is like to solve this term as a non-autonomous.
Okay.
And then this term is frozen in time. And automatically, doing this way, the scheme, the scheme conserves keeps the order of the splitting method. You have a fourth order method, this will be fourth order method. But you need to solve this non-autonomous problem up to this order. But with this procedure, even
and here is something that I don't understand, because normally if you look at the Schrödinger equation, Gross-Pitaevskii equation in the frame, the solution is exponents to this thing in the
which one is
right. The solution it would be, and then no, maybe okay. I think I know what.
And this scheme is that I didn't want to get into much detail because it was not necessary for this talk. But really, this kind of aberration corresponds to solve this equation, a non-autonomous one and a slightly different one. Sequence notation.
Okay. Thank you. I know I understand.
So for your optimal control, you were mentioning that you would like to linearize. Do you have ideas how?
Well, perhaps using similar techniques to this one. Well, maybe from previous step or from if you store from each iteration, one has to we need to solve this equation. Suppose that we integrated, we start with an initial guess for this value, for this function, because this has to be done iteratively, because we don't know this final condition. Suppose that we start with an initial guess here. We integrate forward. We will reach to one point where this is not exactly the solution we want, and then we will not obtain, this will not coincide with this. And during this process, we have evaluated these terms many times in the whole process. If you store this, in some sense you have a time dependency here, because these are scalar numbers. Perhaps this can be used. If you store this time-dependent function, maybe for the next iteration you can use it for previous ones. So in some sense this will be a linearization when you repeat the second iteration, because you have computed many things. Perhaps if you are relatively close to the convergence, maybe you can store these scalars, because these are a scalar value, it's not a wave function. Maybe these values can be kept in the next iteration, and then in this sense this will be a time-dependent problem. It will be linear. So, but it's an open, yeah.
What about integrable subcases? I mean, integrable in the sense of soliton theory. For instance, if the potential V is 0 in Gross-Pitaevskii, cubic nonlinear Schrödinger, is integrable discretizations of any, are integrable discretizations of any use? Are they competitive in this field?
I think it will be difficult for solitons to use these kind of tricks, and that they would keep the soliton. I'm not sure. I have no experience in this.
I mean that there are some integrable discretizations,
Yeah.
and are they useful from the numerical point of view, or are they competitive as compared to this method?
I mean, like Tableau with Sladik and things like that.
Yes, or Suris probably.
Yeah.
Not so much.
Well, they are for constant time-independent potential,
Of course.
and they have much lower accuracy. They have wonderful features. You can prove nice theorems. And I think that there is a big gap. For example, Gross-Pitaevskii has a Hamiltonian function, time-dependent Hamiltonian, but still has Hamiltonian energy. What is Magnus doing to the energy? And I don't think anybody knows.
Linearizing is going to introduce time dependency, but maybe you destroy a little bit the energy preservation, but maybe don't destroy much, and maybe it's bounded. The errors.
But is it ergodic?
Yes.
We don't know. Further questions? Okay, no, thank you again.